Hi, I'm Pari Singh. The talk today is about lessons we can learn from other industries in how they've sort of approached systems engineering and systems mindset. The goal today, I will talk to you about specific learnings and specific ideas and specific tips, but the goal today isn't really about that. The goal today is about sharing some stories in how other industries like chip design, industries like gaming, industries like software engineering, have gone through this transition of dealing with massive complexity systems and massive complexity products and how they come out on the other side. My secret goal is to inspire curiosity. So a few people from here can go away and start learning about these industries and specific things that these industries have done to deal with systems complexity. Press a button. There you go. So quick background to me. I am not a systems engineer by training. I'm a mechanical engineer by training that has sort of come into this world. I was trained as a mechanical engineer in the UK at Imperial College. And back when I was a kid, we started designing little scale hybrid rocket engines for fun, 1 kilonewton to 5 kilonewtons. And as things became more complex and we needed more people to do that, we started building tools to better integrate the worlds of planning and systems engineering and engineering. That has ended up rolling into my day job, which is a technology startup called The Engineering Company. And we build tools to better integrate the world of systems engineering and mechanical, electrical, chemical engineering. My day job means that I run a software company. And I really go deep into how software development processes, how agile, how CI/CD work. And also our investors include people like the CEO of Unity, which is the largest game engine in the world. So by chance, I've had the luck of going really deep into several different fields of engineering that aren't necessarily hardware engineering. And there is just so much we can learn. So a quick primer. We're in this transitionary period. The SR71 Blackbird, I'm preaching to the choir here, is one of the best products ever created. We were able to go from an idea to a design to manufacturing methods to putting this to flight in something like 18, 22 months. We were able to move incredibly fast. And we were able to do that because the SR71 frankly had smaller amounts of complexity and much more importantly, lower coupling in between the different functions. Today's engineering looks nothing like this. Today's engineering is far more complex, requires far more people, and is a whole different ballgame. This is where MBSE and the whole function of systems engineering has come about. But as we all understand and feel, we're in this transitionary period where we're having some growing pains. We're having some growing pains about MBSE being adopted by the wider community, about how we bring systems engineering into the actual engineering design process, not just at the start or at the end, but all the way through. And I think there are so many learnings we can take from these industries. The chip design industry is a fascinating one because they actually started exactly where we started. In the chip design industry, back in the early days, we had drafters on drafting tables drawing physical pictures of transistors, of how these things came together. And we've gone from that era of 100, 200, 250 transistors on a chip to today's era where we have over 10 billion transistors in an M1 MacBook. And we've done that by doubling the number of transistors on the chip every single year. We're doing massive complexity systems engineering here from a chip design point of view. And the way we do engineering looks completely different today. And the tools we use look completely different today as to what they used to look like. Gaming is another fantastic example where we used to design games like Pong and Tetris and Mario. Very simple games, very clear mechanics. Today we have Call of Duty. We have these massive AAA video games with huge worlds and massive complexity. We've got tens of thousands of engineers from different domains with highly complex couplings between the level design, between the physics, between the sound, and they're able to push out new games every couple of years, and they're able to do that at a massive scale. The software engineering industry needs no introduction. We've invented whole new processes like CI and CD that I'll go into in a bit. I think the most important thing to realize here is that this isn't new. This is a standard transition that every single engineering function, every single engineering industry goes through. And the thing that sort of caught me off guard about learning about these industries is that every single one of them have a systems engineering philosophy and a systems engineering mindset. They don't call it systems engineering. They might call it something completely different, but they all have that, and that's been critical to their success. So the first tip, the first idea, systems engineering needs to be embedded and integrated through the entire life cycle, not just at the start or at the end of a project. A great example of this is the software engineering industry. Put your hand up if you think the software engineering industry has systems engineers. A few. If the software engineering industry has systems engineers in there. Can anyone that has their hand up give me a guess to what the title is for a systems engineer in a software company? Go. Nope. Anyone else? Good guess though. System architect? Nope. It's not got the word system in it.
Business analyst.
We're getting closer here. The real name for a systems engineer in a software team is a product manager. If you think about what a product manager does day to day, they think about the user, they write user stories, they build user specs, requirements, they decompose those specs, and then through the life cycle of a software project, they manage different multidisciplinary streams, front end, back end, cloud, DevOps, to be able to come out with a product that actually serves the functional needs of the user. This transition is a fascinating one to look at. If you look at the older school companies like IBM, companies like SAP, all of these companies had product functions, but those companies weren't really able to deliver good products. And the reason for that is product sat in one corner, engineering sat in another corner. There was a Chinese wall in between them. And product would say engineering's not really delivering to the spec, and engineering would say product's writing me specs that are completely unfeasible. What's ended up happening in modern software companies, think of Atlassian, think of Slack, think of Facebook, is that product and engineering are one team. Product sits inside of engineering, and they're a core collaborator in that process. If you have two different teams with two different agendas, it's not going to work. Systems engineering and mechanical, electrical, whatever engineering really need to be part of one holistic team for this to work. The second big learning, and again in the software engineering industry, is that every single person in that software engineering team must have a systems first mindset. A good example of this is, well, why don't we just talk about systems as a whole? If any element of a system is locally maximized, you're off the global maximum for sure. Another way of thinking about this is if any engineer in a team of 50 or 100 is selfish and says, I want to build the best front end at the compromise of a back end, I want to build the best cloud streaming at the compromise of the user quality, the whole thing breaks and the whole thing goes off kilter. In the software engineering industry, they've invented a term for what they look for in people when they hire them. And they call these people T-shaped people, which is they have the bottom of the T, which is they have very deep competency and experience and expertise in one specific element, back end, front end, cloud. But then they have a very broad, generic horizon on understanding what the other disciplines are and how they might collaborate with those. I see lots of companies building systems engineering cultures, but there'll be one engineering function that wrecks everything. This is really hard because what it says is that every single hire, every single member of the team is important and has a responsibility to the system over their own function, but that's absolutely what's needed to make this happen. This one is about the movie industry. This is a bit of a change of track, but I think it's a really important parallel to how we do stuff and rising complexity. Movies have gone from really simple, low budget, 5 or 10 million budget movies to 200 million or 250 million budget movies. The complexity of some of the stunts that are happening in these movies has gone off the record. If you look at The Matrix 2, this is one of the first movies. They had this huge runway scene, motorway scene, where they had trucks and they had people and they had fighting, and the whole thing needed to be choreographed because you had physical cameras that needed to be in the right position. It was really hard to storyboard that. So they came up and they started to use this thing called previs or pre-visualization, where they got block models and they got a game engine and they started moving around block models to represent where the cameras would go and where the speeds of the lorries and everything else. And they started to invent this idea of pre-visualization, which is basically a digital twin for the most complex scenes in a movie. And what this meant is that the cost of reshoots came all the way down because you were able to get all that risk, stick it in the front end, enable fast iterations, enable mistakes to happen there where the cost of change is extremely low. And that became really common in the industry. So in the 1990s and in the early 2000s and the 2010s, Previz was used in basically every action movie in the world. And it was used because it was such an effective tool that movies had to be able to lower cost. This is MBSE in action. What became sort of interesting is that Previz didn't just stop at specific action scenes. If you look at today's Marvel movies, $100, $200 million budget for every single one, they actually don't storyboard the movies anymore. They do the entire movie in Previz. So back in 2016, they had Avengers Endgame end-to-end shot with block models throughout, with voice actors acting as effectively in animation. And all the kinks and all the issues, they resolved there quietly. And then when the movie needed to be shot, they could do the entire thing because they knew exactly the reference that they needed to do. I think where MBSE and where Previz starts is it's a way of reducing costs, reducing risk. But what ends up happening is it becomes a really powerful tool to give directors and engineers flexibility. If the cost of change is super low, you get experimental, you start trying things that you wouldn't try before. And this single technology has really revolutionized how movies are made. Traceability doesn't stop at requirements. I'm going to use this. There's sort of two contexts of traceability. One is around regulation, which I'm not going to talk about, but one is around being able to understand the what if. And digital twins go straight into this, which is if you're able to understand, I changed this requirement, which other requirements are affected, that's useful, but it's not end-to-end. When we say end-to-end traceability, we have to take that idea of traceability and take it to the next step, which is models, which is actual designs. If we have end-to-end traceability, which is what you're starting to have with Previz, things can really start to change. I think a really important element of this is people think of digital twins as these big, complex boxes, which require a lot of time to be able to set up. But actually, even a crude model that is integrated with lots of different functions can serve the purpose. Previz started with nothing more than just block models representing people and has now turned into something much deeper. The final tip I have is from the software engineering industry, and this is baseline as frequently as possible. The software engineering industry have gone in this really interesting transition from software development teams being in a single room and all talking to each other and all understanding the state of a project, to massively complex systems like Linux being built by tens of thousands of contributors that have never met each other, that don't know each other's names, that don't know what each other are working on, and they're yet still able to make one complex system work. How is that? Well, in the software engineering industry, we've invented this idea of continuous integration and continuous deployment. The whole idea goes, if I am an engineer, I can work on this element of the program, and I can build unit tests, i.e. local requirements, that I check for myself. But when I push my code to the main, a whole bunch of tests run automatically in the background, basic integration tests that are testing if my code runs with other elements of the models. This single invention has catapulted software engineering industry into a new age. Every modern software engineering company in the world uses continuous integration and continuous deployment. And without it, it's basically hard to imagine how you'd build software systems. We are building massively complex systems, but we don't have any of this. And as a result, people are being the continuous integration, continuous deployment, and we're feeling the pains of it. The tip here is to try and find ways to do this as much as humanly possible. That's it. Harry and I are both here. This is our first time at IW, so it's a real pleasure. We'd love to meet any of you and as many people as we possibly can. So if you have thoughts around this, if you've got pushbacks, if you've got other ideas, we'd love to hear them, and we're here all week. All right, thanks very much.